Okay, I don't understand what's going on, but I'm only getting a very small space being recorded, so I'm going to put stuff on top of one another and hope you can deal with that. We want to talk about the torsional or physical pendulum. This box with a pivot right here would be such a physical pendulum that if I pull it over the side to the side so that the center of gravity is not under the pivot point, then you do get this torque, and it would be a restoring torque. This torque would tend to bring the pendulum so that its center of gravity was back underneath the pivot. So you have a situation where I would love it if the restoring torque was proportional to the angular deformation. And we'll find that we can get that to be the case if we do this for small enough deformations. But in such a case, then I could replace torque by iota alpha, and I'm going to put in as a constant of proportionality, if this is indeed a proportionality, a kappa, because it's rotational instead of the K that we used in the translational case. And this, of course, is a differential equation. Let me make that explicit for you, that the second derivative of the angular deformation with respect to time is equal to this quantity, where I've divided through by the iota. And, of course, the solution to such a differential equation is going to be exactly the same as before. Let me see if I can this go away. Yeah, okay, get that out of the way. I will choose a cosine to be the thing I'm going to replace theta by, and if I take the second derivative of that with respect to time, we do get this expression here, which looks very similar to that. And so the alpha can be equal to theta if omega squared is equal to kappa over iota. I will take this opportunity, I hope you can see what this says, but it points out that here you have an omega and here you have an omega, and they clearly cannot be the same omega. This is angular frequency, the derivative of angular position with respect to time. And this is angular velocity. This one is angular frequency. Clearly, they cannot be the same thing. You can't have a thing being equal to itself times some other things. So clearly, angular frequency measured in inverse seconds is not the same thing as angular velocity measured in radians per second, even though we use the same letter omega. All right, so we have that if omega squared is equal to kappa over iota, then you have the conditions for a simple harmonic behavior. And recall that we got from, in the previous case when we were dealing with the translational case, we got that the period of a simple harmonic oscillator would be 2 pi m over k, when omega squared was equal to k over m, and so it follows that by the same derivation, and that's not visible, is it? By the same derivation, we can get that for this rotational simple harmonic oscillator, the period will be equal to 2 pi iota over kappa. All true if this thing is indeed obeying a rotational Hooke's law. Well, let's consider this pendulum. I'll bring back that. And I hope that's visible. Again, the torque equal to kappa times theta, But this time for this physical pendulum, let's consider that torque. It would be the arm crossed with the force. That would be, I'm going to call this H cross mg. And that means hmg sine theta, where the theta would be the angle between the two vectors when they are tail to tail, which we are so pleased to see is the same as the theta that we have deformed it through. And so it follows that I can, we have this expression for small angles theta. If we're measuring theta in radians, I can replace sine theta by theta, and then I can divide out theta from both sides, and we have this expression where I conveniently ignored the negative. Then we'll put this value in for kappa here, and you have this expression, which is really this expression, but then I worked out what kappa would be for this pendulum, and this is something else to memorize. And probably following the derivation would be a very helpful way to make sure you have the right formula. Now let's play with it a little bit. Let's take this physical pendulum and reduce it to a simple pendulum. That is, I'm going to take all of the mass and locate all of the mass at the end of the string. That is, the rotational inertia of this thing is going to become mh squared. But then you can see some very nice simplifications, and we get that if we reduce this to a simple pendulum or an ideal pendulum, then it becomes 2 pi square root of h over g. And I would hope that you would recall from last year that the value we got for the period of a simple pendulum was 2 pi L over g. Isn't that lovely? Thank you very much.